Okay, and now for the second talk by Abhishek Banerjee from Weizmann about probing relaxions at the precision frontier. Please.
Hi, everyone. First of all, I'd like to thank the organizers to give me this opportunity to present my research here. So let's start. The outline of the outline of the talk would be, I'll introduce the topic, and then I'll talk about relaxion, and after that, I'll talk about relaxion dark matter and how to search for them using atomic spectroscopy, and then I'll conclude the talk. So the motivation is the following. We know that there is new physics, but it's not associated with any scale. And for many years, the common wisdom was the Higgs hierarchy and dark matter will give us the TeV scale new physics. But at LHC and direct searches, we haven't seen anything. And that puts pressure on the conventional symmetry-based argument of the naturalness problem. And because of that, like, we have many new ideas that are recently proposed to ameliorate the hierarchy problem. And we used relaxion as a concrete example here, but many of the other solutions in content light scalar, as we saw yesterday and even before. And in this particular talk, I'll focus on the phenomenology part. So we'll not discuss about the relaxion in the context of multiverse or in anthropic solutions, how to populate the vacuum. We can see like Judici et al. for a discussion on that. So the bottom line below is that the relaxion is an axion-like particle, which is described as a scalar which has the mixing with the Higgs, and it has some weird shallow potential and the unknown mass. So now I'll briefly go over the relaxation mechanism, the relaxion itself. I'll talk about I'll just focus on the GKR part, inflationary-based relaxion. So what it is, it's a dynamical ameliorations of the Higgs hierarchy problem. And it has three crucial steps. The first part is we make the Higgs mass, Higgs mass parameter. It depends on the scalar phi. Phi is relaxion here. Lambda is the cutoff of a theory. And I call these combinations as the Higgs mass parameter mu h square, which is a function of phi. And so that's the first part. Second part, we add a potential to the relaxion, which can be written as like the way here, which is lambda 4 over the F effective times phi. C is like an order 1 number. And the third part is we add a Higgs dependent back reaction wiggle potential, which I have written here as mu back reaction squared, and it depends on the Higgs wave. This is Higgs wave squared times cosine phi over F, which has the wiggles. And in this setup, the hierarchy problem is to understand why the Higgs mass parameter today is much, much less than the cutoff scale, which is lambda. So here it's a cartoon of the phi, the potential of phi as a function of phi here. And the right-hand side, it is the Higgs part. So what happens, at the mu square, we start with a positive Higgs mass parameter, and the field phi, it rolls down because of the linear potential till the mass parameter changes its sign. And the moment, at some point, the mu square phi goes from positive to negative, Higgs acquires a wave, and the back reaction potential, which depends on the Higgs wave, it back reacts to the motion, and it stops if at the point when the first derivative of the potential is 0. And at that moment, we call it phi naught. At that moment, we calculate the Higgs mass, and we get this is of the order of the electric scale. So what's the main point here? So again, it's not good. Okay. So the smallness of the Higgs mass, which is the electric scale is much, much smaller than the cutoff, is due to the dynamical relaxation which happens in the early universe. And so that's the first point. It's not based on any symmetry or anything. And in this framework, we get 1 IR degrees of freedom, which is the relaxion itself. And the mass of the IR degrees of freedom is the electric scale times the electric scale divided by the cutoff part 3/2. And so this is like the second point. And the third point is, oh, there is supposed to be something here, but okay. for low energy, so now we have changed the game from UV. We don't have like now we need to look for IR physics, not UV. And for low energy phenomenology, what's most important is to know the mass and how does it interact with the standard model. Okay, so the next line, which is supposed to be appear here, that both the informations we get from the back reaction potential, which depends on the Higgs wave, but that is like a bit simplifications of the whole thing, because we have shown that it's the relaxion itself. Relaxion is also relaxed, and it can go and so the conventional naturalness argument that the mixing angle has to be less than the mass over the Higgs wave doesn't apply. And I'd be very happy to discuss that, but I don't think I'll have time to discuss that part. But it was supposed to be here, but it's not. But I hope it's okay. And so that part is okay. Now, so from this point onwards, we can just think of relaxion as a Higgs portal model, which interacts with the standard model through the Higgs mixing or mixing angle here, sine theta h phi. And in this Lagrangian, we have written F, it's the fermionic field, and capital F mu nu is the electromagnetic field strengthener, and G is the gluon part. So this is the low energy phenomenon, low energy effective interaction. So this plot is just to show you what we have got here. I have plotted the relaxion Higgs mixing angle, or the mixing angle, in the horizontal, in the particle axis, as a function of the mass in EV in the x-axis. I don't want you to understand each and every part of it, but to focus on the fact that in order to just search for one scalar, we need to search across frontiers. For example, if we are interested, if we are focusing on the region around GeV, we need collider searches compared to the ones if we have in the sub-EV range, then we need something else. So that's another thing that requires our attention. That okay, new paradigm, new technique, which is important. So that's the one part. And the second point here is in both the axes, we have 30 orders of magnitude. It spends it covers 30 decades in the parameter space, which is another, you can call it opportunity, you can call it crisis, it's up to you, but this is what we have. Okay. And I'll focus on the sub-EV part of the parameter space. Now, the first question that you can ask, is, we have got a scalar which mixes with Higgs. Now, what else does it do? Can this be a viable dark matter candidate? That's the question we asked. And as you can see from the little brown triangle here, that it is. So I'll discuss about this, how relaxion could be dark matter. So the idea is similar to the axionic dark matter. Axionic dark matter, the dynamical misalignment mechanism. So what happens after reheating, we had two potentials, the linear and the back reaction ones. So Higgs relaxation happens during inflation, fine. And after reheating, if the reheating temperature is greater than the electric scale, then we have the electric symmetry will be restored. And as a result, relaxion will roll a bit. And so, the rolling of relaxion. But now the scenario is a bit different than the Hubble part, than the inflation part, because now the universe is cooling down, and as a result, the wiggles or the back reactions will reappear at some temperature or time. And if the relaxion is stopped at that moment, then it's not at the minima. We have displaced it a bit, and then it will start to oscillate when the Hubble scale will be of the order of the mass of the particle, mass of relaxion. So this is axion-like dark matter, but this is like a scalar dark matter. Okay, so now this is some details of the model that we worked on, that depending on how relaxion is stopped, we have divided it into two parts. One is like in the minimal model, we just said that, okay, the Hubble friction, the Hubble expansion during the radiation domination is enough to stop the relaxion. We call it minimal model. And for heavier relaxions around the EV scale, we need like some additional frictions, and we provided it with some coupling to dark photon. So these are the two scenarios. So now here I have plotted the mixing angle as a function of mass, and for relaxion dark matter. Now you say that we have two distinct regions here, and the one at around the EV scale, and the other one is around 10 power minus 11 to 10 power minus 6. The red lines indicate the time when the wiggles reappear. These three lines, this is for 5 GeV, this is 150, this is 15, but you know, it's so the triangle is this one that I showed before, and this part requires coupling to dark photon. Okay. So now take a step back and think what we have got here in our hand. We have got a coherently oscillating relaxion, which can be a viable dark matter candidate in these two regions that I said. And it has interactions with the standard model, like a scalar interactions. The question is how to search for such scalar relaxion dark matter. And from this point onwards, I'll talk about searching for scalar dark matter in general. Relaxion is definitely a subset, but there are other candidates in literature. Why my citations are not coming? But anyway, so. Okay, there are, for example, dilaton dark matter and other candidates that we have. So for low energy theory, we can write down an effective interactions can be written in this form, where we have written the field phi weighted as with mass of Planck times the interactions with the light fermions, with the electromagnetic field, and the strong field. And the scalar has an oscillating background where the oscillation amplitude is given by the dark matter density over the mass. And this has this oscillation has profound implications that all the constant in nature, they are oscillating at the frequency which is equals to the mass of the field. The mass of the fermions, the fine structure constant, and the strong coupling constant. And so now the question is, how can we search for, like, these oscillations can be searched in experiments which are looking for the direct time varying constants. There are such experiments, and we have denoted them as direct dark matter searches. What are the examples? So clock experiments like atomic and nuclear clock, gravity wave detectors, mechanical resonators. Yesterday, day before yesterday, someone was saying this. So these are the possible ways you can detect them. So what's the strategy? What's the strategy to find such oscillations? We take two systems. Okay, I thought some question. Okay, so we have two systems. Let's call them system one with the energy level difference. We have an atomic system. Okay, we are looking at the transition frequency, like two atomic systems. Let's call one as the energy level difference is delta E1 and corresponding frequency is F1. And the second one is, let's say, delta E2 and the frequency is F2. And for simplicity, let's assume that the dependence of F1 and F2, they only depend on alpha and ME, but in general, they depend on all the fundamental constants. And how is the dependence? F1 depends on alpha to the power xi alpha 1, ME xi ME1, and for F2 is alpha xi alpha 2, ME power xi ME2, okay? So that's the dependence. And then what we do, we look for fractional change in the frequency ratio. What it means, we look at the ratio and then change of that divided by the ratio itself, F1 over F2. And this quantity, delta F1 over F2 divided by F1 over F2, can be written as delta F1 over F1 minus delta F2 over F2. And as you can see that the change in F1 is coming from the change in the fundamental constants. So this formula can be just rewritten, re-expressed in the form of delta of Q tilde I 1, 2. 1, 2 represent two systems. Q tilde I are the sensitivity coefficients corresponding to one particular fundamental constants, or these are also the xi's here. So the difference of the xi's times the corresponding coupling constant D times phi over the mass of Planck. What are the examples of it? We can take two systems as like two clocks, okay, clock cavity comparisons. Let's focus on this just to get an idea what am I saying. Let's say that the system 1 is an electronic transition in an atom, and electronic transition in an atom depends on the Rydberg constant, which is in the leading order can be written as the mass of electron times alpha square. So the variation of such transition, delta F1 over F1, can be written as the 2 times the variation of alpha plus 1 times the variation of ME. And for cavity, the gravity modes, the frequency of it depends on the length, and length of a solid body, it depends on the Bohr radius. And the Bohr radius can be written as the mass times m of mass of electron times alpha power minus 1. So the variation of the cavity modes, delta F2 over F2, can be written like this. Now, when we compare a clock with cavity, I'm not sure whether people can see it, but okay, there are 2 lines down. You can't see it here. I don't know why is that, but okay. So what's written here is the following, that when the cavity is active, that means you still get something from the cavity. So you subtract the F2, delta F2 over F2 from delta F1 over F1, and you see that when the cavity is active, you get that the Oh, nice. So you see that when the cavity is active, so the comparison test will be only sensitive to the change in alpha. And when the cavity is frozen, that means it's not responding anymore, then this comparison, delta F1 over F2, the fractional change of the ratio, is sensitive to the linear combinations of 2 constants, okay, 2 coupling strength. Okay. So there is another test which constrains the scenario, the presence of a light scalar. It's called the equivalence principle test. So what happens, it doesn't depend on the dark matter. So what happens if you have a scalar, it can also mediate some long range force, the Yukawa potential, the Yukawa force, and that also constrains the scenario, okay? And these are called the equivalence principle EP violation tests. And it measures the differential accelerations between 2 test bodies in the presence of a source, okay, fine. And what the measure is called something called Etwas parameter. The first paper on this was written in 1922, which is like 100 years ago. Okay, anyway, so Etwas parameter is something which is like the differential acceleration divided by the average acceleration of 2 test bodies, A and B. And this parameter, eta EPAB, is proportional to something called the diletonic charge difference of 2 bodies, delta Q, times di. These are the couplings, times the diletonic charge of the source times the coupling. Okay, and the ith diletonic charge of a body X can be thought of the fraction of a mass coming associated to that particular constant, fundamental constants. Okay, so d ln m of x, the mass of the body X over this. What are the examples of it? There are one experiment is called microscope experiments. This is measuring the differential accelerations of 2 test bodies made of platinum and titanium alloy. And there are other experiments like, they're measuring the 1 test body made of DE, other TI, and all such tests. I told you, like, it's 100 years, so there are so many tests. Now let's go back to the parameter space where we started. So again, this is sine theta, this is mass. And you see, okay, we have, so these are all direct dark matter searches that I was mentioning. SR SI, for example, it's a clock and a cavity comparison test. These are DY and RBCS is like, these two are clock comparison tests. GO600 is a gravity wave detector. Those can be used, and this is a projected bound at that point. And the red dashed line is the nuclear clock projection on this. But I want you to focus on the fact that the fifth force constraints are really strong. Like it's very difficult. Like the direct dark matter searches are good or fine, but fifth force have already excluded a large portion of the parameter space. Now the question is there any way that the fifth force and the direct dark matter searches are giving us complementary informations? Or other way to phrase the question, is there any way to sort of bypass the effect? And I'm going to argue in next 2 slides that in fact it is possible that these 2 tests are giving us complementary informations. Why am I saying this? In the following reason. As I said, that the direct dark matter searches are, we do like the fraction of the frequency change, and the EP violation tests are, they are sensitive to the diletonic charge difference. So you can think of, we have a 5-dimensional vector space of couplings, because 3 to the like DME, like up quark, down quark mass, and the electron. 1 to the alpha, the change which is responsible for change in alpha, and the other one is to the gluon coupling. So we have 5-dimensional vector space, and in this vector space, in this 5-dimensional space, the EP test and direct dark matter searches, they constrain very different linear combinations of coupling. Okay, what I meant by that, for example, if you take microscope experiment, which is comparing the differential accelerations of platinum and titanium alloy, it constrains a linear combinations, which is written like this. And clock cavity comparison test that I showed as an example, it constrains like a 1 and 2,1 in this vector space, in this notation, okay? And if I give you a 5-dimensional vector space, then you can tell me that, okay, definitely there will be at least, we can find directions which would be orthogonal to 4 such vectors. So we can take 4 EP tests, 4 equivalence principle tests, and I can find a hypersurface which is orthogonal. Like these EP tests are blind to that directions, and that directions in which the orthogonal directions can be written like this: Q hat full, which is the unit vector in this case, it is given like this. Okay, this is the vector. So what is the bottom line here? That models of scalar dark matter with coupling directions, which is defined according to Q hat full dot D, D is the coupling, would not be constrained by these 4 leading EP tests. So if you are writing a scalar dark matter model, according to this, the Q hat full dot D, then you will not have the first 4 EP bounds will not constrain you. Just to support my claim, it's a very messy plot, but this is a plot where I have projected, this is the mass coupling to the mass of electron as a function of the mass of the field, DME and the mass. So what we see, like in the solid lines, we are only considering models where DME is non-zero, which is like in the literature, this is the case. Most of the times we switch on only, like when we plot the this exclusion plots, we switch on only one coupling and then we see, okay, what is going on. So this is what I did for the solid lines. And you see that the EP bounds, okay, BETI, BEL, CUPB, microscope, these are all EP experiments. You see that, okay, all these bounds are present. And in red color, in blue color, and in, okay, brown color, I have written like 3 direct dark matter experiments, such as like clock experiments. So this is CS cavity, like these are some other experiments. Forget about that for a second. And you see that, okay, these experiments are losing to the equivalence principle test by a lot, like when you have only one DME is non-zero. But then if we switch on, if we define our parameters the way that Q hat full dot T is switched on, then first 4 EP tests are not there, it's blind. But the 5th one, which I wrote as BECU, it's still there, which is the black dotted line. And so it is reduced by 3 orders of magnitude, and as a whole, the EP tests are 1, 2, 3, 4, 5. So EP tests are mitigated by 5 orders of magnitude in this plot, and the clock experiments, they suffer the it's just a factor of 2. So yeah.
Where are stellar cooling bounds here?
Star cooling bounds are like it's 10 per minus 7 eV. Star cooling bounds are important, like in the it's not in this part of the.
It's not clear to me because the effective scale, you're showing 10 to the 12 there, so I don't know if for BME.
We can just go back here in the actual plot. You see, just a second here. So star cooling bounds, it goes like this, straight. This is the star cooling bound, astrophysical bounds that I wrote. It goes like this. It's very small. It doesn't affect. It's okay. It's there, but it's not the strong effect. So, well, I don't know where I was. Here. So this is like, I'm not saying that, okay, first of all, we have mitigated the effect of EP by 5 orders of magnitude. That's a good thing. But still, the equivalence principle test gives you the strongest bound. That's first thing. But now, if we improve these the clock experiments by 1 or 2 orders of magnitude, we'll be going to the uncharted territory for in the next future. And as you might know, that in last 2 years, I don't have the plot here, but last 2 years, the experiments have gone they have improved by at least 2 to 3 orders of magnitude. So hopefully, in near future, the direct dark matter searches or the time varying part, they will find some parameter space which was not excluded by the EP test. Okay. And that brings me to my conclusions that the null results at LHC and other direct dark matter searches are calling for new theories and diverse experimental approaches. And scalar dark matter can be probed by spectroscopy. And there is a way to sort of bypass the EP bounds, which were the constraining factor on these models. So, yeah. Thank you very much.
Thank you very much. Questions?
Simple question. How much of this depends on phi being the relaxion?
Well, it's I just talked about the dark matter part. It's a scalar dark matter, and relaxion is an example of it. But if you look at the part of the plot that I showed, it's actually it goes you can just apply this technique in any part. But for relaxion, it's a bit of a problem in a sense that you can think of it's like a Higgs portal case, right? That I was arguing. So for that, it's really difficult to get the hierarchy between, it's not a hierarchy, but I showed you the direction, right? This Q, sorry. See, I showed you the directions Q hat full, right? So you need to sort of align your directions like this. But for relaxion, the dependence of, let's say, coupling to gluon and coupling to electron mass is well defined. For relaxion, it's actually a very interesting case in a sense that, okay, if you can achieve this hierarchy that the coupling to electron mass is very high compared to the alpha for relaxion or for any Higgs portal model, because it's suppressed by, it's the triangle diagram, right? So it's suppressed by 1 over alpha, compared to mass, it's 1 over alpha, so which is 100. So it is possible, but for gluons, it's a bit of a problem. So yeah.
Can you show your plot, the last plot you showed?
Here?
Yeah, this one. So in the frequency regime, between 10 to at around 10 to the minus 12, there are also other exclusions, right? From Origa, from DME.
It's here.
and there is also LIGO searches.
LIGO, I think it's not the, okay, Origa is here. I should have put it here. It goes actually below. Okay, it's quite sensitive. LIGO is not, but I think this experiment A that I'm showing, it's more, how do you say, it's the strongest one. If I have a backup plot. But
also, the cooling bound actually from red giants is DME. It's 5 times 10 to the 6.
5 times 10 per 6.
Yeah.
Like it's here.
Yeah, it's right there.
Okay, I need to check, but okay, thanks. That's for DME.
Yes.
So it's like what it is in 5 G5EE. Okay. So you are saying that for DME it's 5 10 per minus 6. So
5 10 to the 6. Sorry.
Sorry. So DME over M Planck ME is G5EE. So it will be, okay, might be true. So it's a factor of 10 per minus 21, 10 per minus 21 times 16 per minus 15. Okay, might be true. Okay. Sorry, I missed that. Okay, thank you.
Other questions? Maybe from Zoom? Okay, I have one. Can you go back to the parameter space that was with the mixing Relaxion Higgs?
This one or the other?
For example, this one. So here we just heard from Enrico's talk before you that including axion fragmentation, which is not an option, the parameter space that gives you a solution to the hierarchy problem changes. So I guess this would imply that the green line moves somewhere, and in particular the F equal M Planck. And I wonder, I mean, can you elaborate on how they move and how the Relaxion dark matter thing moves, if it moves, which is less clear to me?
I think the situation, the scenario that I was discussing here, it doesn't apply because for fragmentations, I think the mass range of the relaxions that they are talking about, it's around KeV scale. If I remember the paper, so it's not in the same part at all. Okay, and I am considering a slow, like I'm considering during inflations, the relaxion is moving, it's having a slow roll velocity, which is completely different from their construction. So it doesn't apply. Okay. Right?
Other questions or comments?
But yeah, I think well, we can say a bit things, but in the leading order it doesn't. But in that case, yeah, it'll be a bit, yeah, it's not it's like if you consider like the relaxion dark matter that we are considering, it's a wave-like thing, right? Sub EV. So we cannot even apply the same scenario here in this context. And you can still, I think in their constructions, you'll also find some dark matter, which is particle-like, where the reheating temperature is 30 MeV or like around GeV scale, right? If I'm not wrong. So, and I'm talking about the restored, like, the reheating to be higher than the electroweak scale to start with, because I want the symmetry to be restored to start with. So yeah, it's a bit of it's other construction, yeah.
And we can flow directly into the general discussion if there is any question for either Abhishek or Enrico. I don't see any. So let's thank both Enrico and Abhishek again.